Chapter 11, Fluids. First off, what is a fluid? Growing up, my mom would say whenever I started to not feel well, oh, make sure to push those fluids. And she meant to make sure I'm drinking lots of water and orange juice. But if I wanted to be snarky with a physics answer, I could have said, guess what, Mom? I am. Because fluids, in physics terms, can be a liquid or a gas. A fluid is anything that flows. So I hope that you'll keep that in mind, that fluids here can refer to liquids, but can also refer to gases. And before we get into a closer look at fluids, I have a question to pose. So this is a classic question. What's heavier, a ton of bricks or a ton of feathers? And you might be tempted to say the bricks, right? Especially with this image of a single brick and a feather, where a single brick is definitely heavier than a feather. But if you have a ton of each, they actually weigh the same. So what is different about them if the weight's the same? Because materials are obviously different. Well, what's different there is going to be the volume, right? In order to balance out an equal amount of each of weight, you're going to need way more feathers, right? Super compressed together. Versus bricks, you don't need that many in order to balance the scale. So with fluids, we'll see that volume is an important consideration. It's not just about weight, but volume. And volume is closely related to the mass and the weight in something known as the density, right? That bricks are more dense than the feather. They have more matter in a smaller space, a smaller amount of volume. So our definition of mass density, which sometimes is just referred to as density, is the mass of a substance divided by its volume. And so the symbol we use for density in physics is the Greek letter rho. I try and draw it as an extra curvy p to make it clear that it's not a lowercase nor an uppercase p, because we will use those as well for other things. So whatever will help you in noting that this is a separate symbol from p. So our mass density is the mass divided by the volume, and our SI units will follow that exact procedure, right? Where the units of mass in SI are kilograms, and for volume, the SI unit is cubic meters. Since our SI unit of length is the meter, we can cube that for volume, right? Volume, you can picture if it's a cube, length times width times height, that becomes meters times meters times meters. All right, so with this definition of mass density, we can calculate a number of things. We also can figure out what the mass density is for various substances that are out there. So this is provided for you in table 11.1, mass densities of common substances. So we have solids, right, like aluminum versus brass, concrete, diamond. Gold is actually really dense. That's interesting. Lead is as well, which is one reason why lead is often used in weighted materials, perhaps coverage that you don't have lead poisoning. But we also have liquids here, right? There's blood and water, and this also highlights that saying you may have heard before, blood is thicker than water, because it's actually more dense than water, right? 1060 versus 1000. And this water value is one that pops up a lot. It's written as 1.000 times 10 to the 3 because it has all those significant figures. But you can think of it as 1,000 kilograms per cubic meter. And that's one that we will definitely be seeing and using. On various homework problems, if it mentions that you're in water, you can know, oh yeah, density of water. I can look that up in the table. So you don't have to memorize these things. You just have to know that you can look them up as a reference. All right, let's try an example. Blood as a fraction of body weight. So the body of a man whose weight is 690 newtons contains about 5.2 times 10 to the minus 3 cubic meters of blood. A, find the blood's weight, and B, express it as a percentage of the body weight. Right, now as we're looking at this, first we need to figure out what's been given to us. Right, so we have the 690 newtons, and that's just going to be the total weight of the man. So I can draw that as W total. Sorry, that got a little messy. And then we have this other number, 5.2 times 10 to the minus 3. What quantity is that? The units here help us out because we notice it's cubic meters. Cubic meters are units of volume. So that is a volume. Right, so we know those things. Anything else we know? There's one other thing that's highlighted in the problem, and that's that we're focused on blood. Right, so since they mentioned blood, we can go, wait, blood was in that table, right? We can look back a slide and see that we have the value of blood as 1060 kilograms per cubic meter. So that would be one other thing we could add. Since it mentions blood, we know the density of blood is this 1060 number. So rho equals 1060 kilograms per cubic meter. All right. Now we're trying to find the blood's weight in part A. We know the blood's volume and density. Can we get the weight? Well, let's brainstorm a bit. How do we calculate weight? Well, we know weight is going to be equal to mass times gravity, right? So if we can just get the mass of the blood, we'll be in really good shape to multiply it by this 9.8 times 9.8 meters per second squared. So how can we figure out the mass? Well, that's where our definition of mass density comes into play, right? If we know that density is equal to mass divided by volume, then if we want to get mass by itself, we can just multiply both sides by volume. Right, and so then the volume would cancel. On the right, on the left, we would be left with density times volume. So our mass is equal to that density times the volume. And that's something that we can then take and substitute it in over here. Cool, so that will be a way to calculate weight. What if we want to find a percentage? Well, if we want a percentage, we're just going to need to take a ratio and multiply that ratio times 100. So that will be the weight of the blood relative to the total weight of the person. And then multiplied by 100 to make it a percentage and not a fraction. So if the weight of the blood comes out to exactly 690 newtons, then it is 100% the weight of the person, right? We can imagine some other fractions within there. But that should get us through. So let's take a look at the actual plugging and chugging of this. There we go. So mass is equal to volume times the density. So we have that volume in cubic meters times the density in kilograms per cubic meters. That comes out to 5.5 kilograms, pretty solid. The weight is just that 5.5 kilograms times 9.8. So it comes out to 54 newtons. And then for the percentage, we'll take that 54 newtons divided by 690 multiplied by 100. So it comes out to 7.8%. So not a huge percentage, but definitely a noticeable part of your overall weight. So blood is part of your weight. Pretty nifty to see that. And more importantly, this highlights how we can use density to often figure out mass. So that's something that we will often do with these types of problems.